All right, in today's video, we're going to be talking about calling functions, a little bit about segments, and then some of the memory layout, as well as debugging. So we're really going to start to get into our assembly programs and some things that can help us along the way. You'll notice as you start working with the files and the examples that we're looking at, that template that's generated, there's these segments inside of it, .data, .bss, .text. And what those segments allow us to do, or allows our computers to do, is to map out certain sections of a program into memory and then allocate that memory in a way that they can, the operating system can control the access to it. It's important that when we run a program, that section in memory that contains the executable code, the instructions, is read-only. And we don't want to be able to allow other programs or malicious input, for example, to be able to modify the execution of that program, to change the instructions that are there. If you look at one of the templates then, you'll see here, and this is a sample template, you'll see segment, .data, .bss, and .text. And so the .text section is where our code goes, and that's where we have been, where you've been looking at it, and where this week we'll start writing some code of our own. And so those are the instructions. When this program gets loaded into memory, the operating system will know to start here in order to start executing things. The data section is used for string and global variables. It's initialized data. And so what it means when I say that it takes time is that when that program is run, it has to load not only allocate memory and space, addresses and space for it, but it also has to write data into those addresses as well. And so it's not just saying I need 10 bytes for a char array, but I need 10 bytes, and because it's initialized, I'm also going to write those values into memory. So load those values into memory. Right, so the permissions in that section typically are read and write because we need to read content and also write. The BSS section is uninitialized variables, and so if we want to create, let's say, a variable and it's a buffer for something, a char array or some values to store something numeric, we will initialize that. We will essentially request the space in memory, but we won't actually put any values there. And so if we have a buffer and we say we need 10 bytes for this buffer, it's allocated. We're given 10 bytes. We're given an address space of 10 bytes for those 10 bytes, but we don't actually put any data there. And so it's a little bit quicker. And so as you're creating, we're starting to create essentially variables depending on their use, that we're going to put them in the appropriate section. Initialized values will go here. Uninitialized values will go here, right? And if you're going to create a variable and you're going to set a value later on, then you might as well make it uninitialized because you're going to end up overwriting those to those memory locations anyway, right? So probably the biggest thing right now is just making sure that you're putting as we go through examples today, that when you're starting to create these variables, that you're putting them in the correct location. All right, so let's start talking about executing functions. We've looked at some simple code. We've just been moving data around to the different registers, and we haven't done anything that's been all that, altogether all that useful. And so we're going to start executing functions. We're using, and if you look at inside of that sh file, which is, let's see here. So let's just do a cat on video.sh. You'll see that we're using asm_io. And so there's some functions, some library calls basically, like print string and read int, that we're going to use that are essentially, we're linking to those files somewhere else. And so that's why you're seeing, that's why there's this sh file, and that's part of what all these commands are doing. Because we're using asm_io that was created by the author of the book to call some of these functions. So that's where they exist. We haven't defined them. We're using them because we're essentially using them from another library. When it comes to calling functions, there are some calling conventions, and we'll talk more about those later on in the semester, as well as if you take the reverse engineering course, we get into much more detail about the calling conventions. What calling conventions are defining is how, when we call a function, how do we pass data to it? And later on in the semester, we'll spend a lot of time talking about the stack, because a lot of arguments, a lot of values that are passed to a function utilize the stack. For these examples, for these functions, it's a little bit different. We're not using the stack quite yet. And so what we need to do then is we need to use certain registers. So when we call print string, what print string is going to do is it's going to look for the address of the thing to print in EAX. And so we'll define a string, and then right before we call print string, we'll move that address into EAX and then call print string. strings in C, and particularly now in assembly, is what this function is looking for is a null terminated string. So what does that mean? Well, it means that it's looking for a series of bytes starting at the address that we tell it to until it reaches a null byte, until it reaches a 0, 0. And so when you look at strings in C particularly, that's why that null byte is so important, because what this function is ultimately going to end up doing is moving byte by byte, checking to see if it's a null byte. If it's not, it's going to print that string and it's going to continue to read. If we forget the null byte, then it's going to continue to read until it finds what it considers a null byte, which would be that 0, 0. And so that can cause unexpected behavior in a program, that can cause program crashes. The address, right? So we're thinking about pointers, and a pointer contains its value. The value of a pointer is a memory address. And so, everything in our program has an address. And so when what we're putting into EAX is that address in memory in order to find that string. So let's look at an example. So I'll define up here in the data section an initialized value. I'm going to declare what amounts to a variable with some initialized data. So we'll just call this hello. I'll say DB, and we'll talk about what that DB, that directive, we'll refresh on that directive here in a minute. And then I'll just say something like hello 314. Okay. Now, how do we make this null terminated? Well, we have to add a comma and then a 0. And so what this statement is doing is it's essentially allocating a byte for each character, DB. Remember, DB defines a byte, defined byte, and then the comma defines one last byte, and in this case we make that a 0. So that ends up being our null byte. So in order to call print string, okay, we'll go into our text section where we write our code, and we'll move into EAX the variable hello, right? And this moves address of hello into EAX. Okay. So we have EAX set up, right? We have to put the address into EAX before we call print string. From there, we call print string. Okay, and then we can save that. And I save that as video 9. And we can go back to, I'm going to use this video or this terminal session here, and we can run that program. So first thing is we need to build it. And the next thing then is we can run the resulting output. Right, and there we go. Right, so we got the program to print hello 314 exclamation. Now there was no new line, and so that becomes an additional byte that you need to define. The trick to this is you can't do \n. If you're used to format specifiers or printing strings in C, that would be the ASCII character for the new line, in which it would in fact print a new line. If I do that, so I'll save it and we'll run this program again, you can see that it actually just prints \n. It doesn't interpret that as the appropriate byte. And so how we get that is that we have to print the actual value. So we have to say 0 by, I think it's A. So let's try that. Okay, and there we go. So that printed. If you're not sure, go to the ASCII table. And we can look for a new line. So here's our line feed, and here's the hex value for a line feed, 0A. Okay, and so we just a comma separated list of values, and that becomes our string. So this is a variable, this is a label, and it points to a memory address where this stuff, these bytes were stored in memory, right? So we move that address into EAX, and then we call print string, and now we're able to print. Okay, if you forgot the null termination, that may or may not be a problem. It depends on what's there. So we can remove that null terminator, that 0, and we can run our program again. It may or may not work. We'll see what happens. Right? It worked this time. What happened though is that as we're printing, it didn't see a 0 here, it just keeps reading into memory. And we're going to talk about memory. I'm going to break this topic up into 2 videos. We're going to talk more about memory in the next section or the next video. But it just keeps reading until it happens to find another null byte. It happens to find another 0. And in this case, it did that without crashing. That's not always going to be the case. And so sometimes what will happen is you'll say, well, this worked for me, but then I'll run it. My memory space will be, the data that's there is going to be different, and it'll crash. And it'll crash because you didn't properly null terminate. Right, so experiment with that, but for sure, when you want to print string values, you need to make sure that you null terminate it. All right, how about reading an integer? So we can call readInt, and what readInteger will do is it's a little bit almost like the opposite. We'll call it, and then we'll be looking for the result to be stored into EAX. So we'll have the function call, and then we'll be looking in a particular register for EAX. Now, when we talked about the registers early on in the semester, I mentioned that EAX is oftentimes the register where a function will return a result in. And so you can see this behavior with readInt, and that readInt, once we call it, we're looking in that register for that value. So we'll go back to our program. I'm going to comment out the print string. Oh, you know what? I'll just leave it. It doesn't really matter. I'm going to call readInt, and then we're going to dump the registers, right? Because we're going to look at, this is going to prompt, it's like a scanf, it's going to prompt at the terminal, it's standard in, for me to type in a value, and then it's going to store that value in that register. So we're going to dump that register and see what's... All right, so we'll run the program. Hello 314. You can see terminal, it's waiting for me to enter a value, so I'll type in 1. Hit enter, we dump the registers after that, and we can see that 1 is now in that register. So we can run it again. I can type in the value 99, and there's the result. Right? Keep in mind, this is stored in hex. So even though I typed in 99, thinking in base 10, the system stores that in hex. And so you can see that that value is there in hex. So don't let that throw you off. Right? Now we've read that value in. What do we want to do with it? Well, we have the registers available. We can move that value around. We can move it to a different register. We can do a variety of things. You've been able to read input, and you're going to need to be able to do that for the first lab. Be able to read input, move it into a register, read some more input, and then perform some basic operations on it. Addition, subtraction, multiplication, and we'll go over that portion here in a future video. All right, so some odds and ends with that. All right, so we've got 2 functions that are built in. We got print string and we got readIn. They're not built in. We're able to use those because of asm.io.include. How we generate. So there's this process that we go from source code, whether it's C or it's assembly, into generating an actual executable file. And so we have pre-processing, compiling, or assembling. We have linking, and then we actually have the executable. And we're not going to go into too much detail of all of those, but you should be familiar with them. We'll spend more time, or we spend a lot of time going over those in reverse engineering. And so we have this ability with these file formats called the object. And Windows uses the COFF format, which is a common object file format, and Linux uses the ELF format, executable and linkable format. They're different formats, but what these are object files, and it allows us to take and generate essentially the binary of different libraries and different programs and combine them together. And that's what we're doing here when we run that script. What that script is taking is it's taking different object files, so ASM.io, as an object file, and we're using ELF because we're on Linux, and it's allowing us to combine those 2 together to generate that one executable. So we're taking 2 different things, and we're combining one, whatever your project is .out, which is our executable file, so that we can run it, and then it can call print string and readInt. It's there. We don't define that because we're pulling it in from a different format. We spent some time in the RE course going over at least the Windows format and understanding a little bit more about COFF, and in particular the PE, the portable executable format. Global directives allow functions to be exported. We'll talk a little bit more about those a little bit later down the semester. Global, you can see that global directive here, ASM main, that's important because when we run our program, we actually are, this is kind of, the program starts, and then it needs to know what to call. What's the entry point into our program? And so by exporting ASM main, we're defining that entry point into execution for the program. And then, as I mentioned, the calling conventions, and we're going to talk more about those calling conventions in a little bit. All right, data directives. We looked at these in a previous lecture. We have DB, DW, DD, and there are other ones, but what these directives allow us to do is define a number of bits or a number of bytes. We don't typically think in the bits, we typically think in bytes. And so this allows us to define a number of bytes that we want for initialized or uninitialized values, right? For uninitialized or initialized memory. So we can say, I need a byte. If I want a byte, that gives us 8 bits. We can say, I need a word. DW, define a word, and that defines 2 bytes. And then DD is a double word, and that defines 4 bytes. And because we're working in a 32-bit system, that's typically all we need, because we can only address 32 bits at a time. So as you saw, we can create variables. So I can say variable name or label, DB, and then the following value. What may be a little bit tricky here is if I say, okay, I'm saying define a byte, but I've got much more than a byte here, right? If each character represents a byte, how does this work? Well, what's actually happening then is that when the memory space is allocated for the value that I'm initializing it to, what it's doing is it's using a byte for each character. So this is saying define a byte. I actually get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bytes for this string, for this variable. This is going to point to 13 bytes in memory, and each byte then will contain the character, right? Because we're using ASCII, and because ASCII stores a character in 1 byte, 8 bits, then this works out well, right? We could define W, right? We could define a word, or 2 bytes for each character, but that would end up allocating more memory than is necessary because we only need a single byte to store that, right? So that's actually what this statement is doing. That's how it's allocating the memory based off of that statement. Some other examples then, and we'll use these here in another video. This file here, the sample file, will be used for both parts of this particular content here. All right, so we can declare a variable. So let's just call it var A, and I can say define byte, and I can then store a value in it. I can say var B, and I can define a word, and I can store a value in that. And I can say var C, and I can define that to be a double word, right? And so what's happening then is that as the memory is being allocated for these variables, variable A will consume or point to a single byte. Variable B will point to 2 bytes. Variable C will point to 4 bytes, and then hello will point to the total number of bytes here. So we'd have to count them up again: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total bytes. Right, and we'll come back around to these variables here when we talk about memory, because memory is very important to understand, and how it's being allocated, how we're using pointers and addresses to get to these values. Right, so that's how we're using these directives, at least initially here. Once we define these variables, we'll be able to start using them in our program to read their contents, read these initialized values, to now store values, right? Let's say that we're reading an integer, we read a value, and we want to store that value into a variable. We can do that. You don't necessarily have to, but we can. So as our programs become more complex, we'll see more of that usage of these labels, of these variables, to do that. All right, so the next thing I want to talk about, and let's see, hello is a variable, just to see what's the bytes. Yep, so we did all that. Remember, the variable is just a named address. And so I guess I can't reiterate that enough, is that this variable, this label, all it does is it points to an address. It points to an address, like we saw with this example here, and that we move this address into EAX before we call print string. And so that's really all these are. And it's the same thing with any language, right? Even in C or C++ or something, all those languages are doing is kind of extracting away those details from us, and that we don't, unless we're using a pointer, we don't typically have to think in terms of a memory address, an actual location in memory, because it does the mapping for us. But here we are in fact thinking about addresses, right? And we'll talk about these in more detail. and that this label points to an address, right? Hello points to an address here, and we need to either be able to get the address or the data at that address. Okay, additionally, you can use something called debugging, and debugging becomes a very important process as you're trying to troubleshoot what's going on in your program. Some programs, some environments make it very easy to troubleshoot, to print statements out, to inspect what's going on in your code, values of variables at certain stages of execution. With assembly, probably the best place to start is with GDB. And so some will argue, and I guess I could go either way on this one, that in order to debug your program, what we'll end up doing a lot right now is dump regs. You'll be doing something in your program, you'll dump the registers to try to see what's going on. What happened? What is actually stored in that register? Did you call print string and it crashed your program? Well, maybe you'll do a dump regs before it to make sure that what you moved into EAX is in fact an address to some data that we want to print. So you'll end up using dump regs quite a bit. However, you can use a debugger, and we have a debugger built into our environment, into most Unix systems, Linux systems, called GDB. Before we begin, you'll want to create this file. So tilde, remember tilde takes you to your home directory, and inside of your home directory then create a .gdb init file. And so just as a refresher on how to do that, so if I go cd tilde, that takes me to my home directory. So home mill, you can see it's not actually my home directory, it's a previous instructor's, but I'm using his account now and have been for a year, so it's mine now. We have that directory, and if we do an ls-la, that lists all the contents of it. I have a .gdb init file, so gdb init with a T. And you can take a look at the contents, and if you haven't created it, you can just do nano.gdb init, right? And then just take these 4 lines and make sure that you copy them in or paste them in, whatever you need to do, right? So we get those into there. Once we're done, save it, exit, and you should be good to go. You might need to log out and log back in order for that to take effect under your profile. It's not required here in the near future that you use GDB, but I just wanted to show you this tool because it can be very helpful. As far as GDB then, what we do is we run our program using GDB. So this allows us to essentially step through the program, set breakpoints, identify addresses, and say, okay, execution, when you get to this address, stop and let me inspect what's going on. Let me look at the registers and see what is there. And then from there, you can step through it line by line, instruction by instruction. And so we've got some common commands, backtrace, which will show us where we're at in the call stack. We have step instruction, so that allows us to step 1 instruction forward. C is continue. That just continues running the application or the program until it either hits the breakpoint or another breakpoint or the end of the program. B allows us to define a breakpoint. So let's just take a look at an example. And I'll pull up both of these files here, so our terminal as well as our source code. I'll build this again. I'll just go back to my history to make sure I got the latest version. Make sure that I'm in the right folder as well. Okay. And so now I have an executable. All right, I have video09.out. I can say GDB video09.out. And that'll now run that program in GDB. So let's say that I want to create a breakpoint, which I do, because by default, if I don't create a breakpoint, then when I run this program, it won't stop. So I'll say B, and I want to set that breakpoint on ASM main. All right, so I'm looking at setting a breakpoint so that when the execution enters here, enters 00, it stops for me. So we say B ASM main, and you can see that breakpoint 1 was set at a particular address. Right, from there we can say run, and we hit the breakpoint. So this is telling us that we hit the breakpoint. From there, we can type dis ass, so disass, and that'll give us the disassembly. Right, so there's our enter. We're on push A, and we can see that there's our move. So there's an address into EAX, and then a call to print string. Right, move this label into EAX. This label is just a memory address. It just points to a memory address. So we can see that here. we're moving that address into EAX, and then we're calling this function. Technically, these are the same thing. These are labels, just like this. This is a label. This just points to a place in memory. And so we can see that we're calling that address. GDB is nice, and it tells us that that call is to print string. And so that's showing us the function that we're actually calling. That's showing us the place in memory that we're jumping to execute those instructions to call print string. Okay, BT, that's a backtrace. So we're in ASM main, which is inside of main. We can do SI, so that's a single step. And we can disassemble again, and you can see that we moved our instruction pointer, so EIP, from the push A, which was here, now to that move command. All right, so we can step again. And now let's say that we want to inspect the registers. So we can say I space R, and that'll give us a dumping of our registers. So if we just moved this address into EAX, if we look in EAX, we can see that there's that address. So this is the hex value, and this is what it tries to represent that in base 10, essentially in decimal. In this case, doesn't mean anything because this is an address. Right, and then if you hit C, what C will do is just continue. And so it's going to continue until it either hits a breakpoint, or in this case, because it's running the program, it's waiting for us to put a value in. And then once we're done, it'll run to the end of the program. You'll see exited normally. There's the remainder of the results behavior of the program as we are expecting. Right, so you can use GDB to step through your program, and it's a great way to debug. Again, most will probably argue, or some will argue that it's the only way to debug. Don't do the dump regs thing, run it through GDB. Use it as you see fit. So hopefully you find it as a beneficial tool to help with not just 314, but with your programming in general as you progress along in your career. All right, so that's it. What we'll do then in the next video is we'll pick up with talking a little bit about integers and then some memory layout.